It's a great pleasure to have Salil Vadhan speaking to us today. Salil was one of our own. He was a graduate student at MIT, and once one of our own, always one of our own. He's now a professor of computer science and applied mathematics down the road at Harvard. And Salil has worked on a range of topics, starting with cryptography, zero-knowledge proofs. He really kind of gave shape to the notion of statistical zero-knowledge. He then moved on to complexity theory, where he constructed his construction of expander graphs is a classic. He won the Gödel Prize for it with Omer Reingold and Avi Vigderson. Then he moved on to studying randomness in computer science and de-randomization and so forth. And most recently, his passion is differential privacy, and he's been leading the OpenDP project at Harvard. And his talk will be on yet another facet of computer science. So welcome, Salil. Welcome back.
Thank you, Vinod, for the very generous introduction. It's always wonderful to have an excuse to come back to MIT, and now in this beautiful new building. You know you're getting old when the place where you did a PhD has changed buildings twice since the time. So I was a graduate student in LCS, pre-Stata. About what I'll be talking about. It's actually a collection of topics that haven't been a focus of mine for a long time. So multicalibration is something that has come out of the algorithmic fairness literature, which is not really an area that I work on, but just kind of follow from a distance. And then, as Vinod indicated, I used to work a lot on cryptography. It's been a while, but thanks to a wonderful undergraduate, Silvia Cascoberta, who decided to do her senior thesis with Cynthia Dwork, my colleague at Harvard, and me, and Cynthia's an expert on fairness. I got back into this, and we realized connections between multicalibration and things that I was very interested in 10 years ago, and got me excited. And that's what this talk will be telling you about. And in many ways, this talk and this work I think of as a tribute to a dear friend and longtime collaborator, Luca Trevisan, who was tragically and suddenly taken away from us by cancer last year. And as you'll see, hopefully I'll convey in the talk, I think some of kind of what we'll be doing is somehow trying to realize a vision that Luca had a while back. Okay, so let me begin. It's very much on the foundations side, this talk, but I've added some things in the beginning to kind of at least convey, for those who are on the more applied side of cryptography or security, why we might be interested in these kinds of questions and why they might be useful. All right, and so I want to convey how this concept from algorithmic fairness, multicalibration, actually is also a powerful new tool for security proofs in cryptography. Okay, in a short summary, the way in which it is such a tool is that it enables us, in some, maybe many cases, and hopefully you'll find more, to derive computational security proofs from information theoretic security proofs. And information theoretic security proofs are typically much easier. And then a lot of the hard work of getting a computational security proof is then done by multicalibration. Okay, and so I'm going to start the talk with some older examples of contrasting computational and information theoretic security proofs and earlier cases of kind of how we knew to obtain a computational security proof kind of somehow by reduction to an information theoretic one. So let's start with a kind of very old question in the foundations of cryptography and in complexity theory. It's the hardness amplification question. All right, so I'm given a function, potentially allowed to be a randomized Boolean function, so g from n bits to 1 bit. That's slightly hard on average, and I'll be a little more precise about that in a moment. How how do we construct a harder Boolean function from it? Okay, and so like one example might be, you have a one-way function, and the function g of x is you invert the one-way function on x, and you take some bit of the input. And all right, so if this is what's called a hardcore bit of the one-way function, then little g is already very hard on average. But often individual bits of the preimage under a one-way function are not necessarily hardcore, full-fledged hardcore bits, but might only be somewhat weakly hard on average. And kind of motivated, in fact, by that particular example, Yao gave a method back in 1982 called the captured by Yao's XOR lemma for doing this. All right, so first let's say, to state Yao's XOR lemma, more precise, what do I mean by slightly hard on average? We mean for all efficient algorithms A, all polynomial time algorithms, if I now here capital X is a random input, you can think of it as uniform on strings of length n. It can be another distribution, any other fixed distribution as well. Any efficient algorithm will compute G, with at most probability bounded away from 1. So it'll error with probability at least delta in computing G. All right, and sometimes we'll use the language G as delta hard for that. Okay, so think of delta, 0.1 or even 1 over n or something like that. And then what Yao said, well, one way we can obtain a very hard on average function is to ask our adversary instead to compute the XOR of G on many independent inputs, x1 to xk. Okay, so each of these xi's are drawn from the same distribution as x, but independently. Okay, and then Yao's XOR lemma tells you that the success probability of efficient algorithms tends to a half as you increase k, and it tends to half exponentially fast in k. And then there's some kind of negligible additive term. All right, and so our new function here is a function on k times n bits, that computes the XOR on those k inputs. Okay, so let's first look at the information theoretic version of Yao's XOR lemma and see why it's very easy to prove. It's 2 lines, the proof. I won't give all the details. One way, so what do I mean by the information theoretic version? I mean, let's remove the polytime constraint in both the assumption and the conclusion. We say for every A, the probability you compute G is bounded away from 1. So for this to make sense, G can't actually be a deterministic function, because if you have unbounded computing power and G of x is determined by x, then given x, you can compute with probability 1. So here it's really important that we think of randomized functions. Okay, and the randomness of the function is the only source of hardness here. All right, so then you can actually just write a simple formula for the maximum success probability of any efficient algorithm. All right, it's going to, one expression for it that's very convenient for proving the XOR lemma is a half plus a half times this quantity here. It's the expectation over inputs of an expression here that's the bias of G. G, remember, is a randomized function on that input x. All right, and so you could write in this form expectation over the randomness of G of -1 to the G of x. What this is just doing is taking the absolute value of the probability that G is 1 on x and the probability that G is 0 on x. Okay, so if G of x is determined by x, this quantity is 1. If it's a coin toss, it's 0. Okay, and then we just observe, if you look at -1 to G of x1 plus XOR G of x2, and so on, that just becomes a product of -1 to the G of xi for the different xi's. And then you just do a little algebra, and you get exactly this exponential decay that we wrote here. Okay, really easy proof once you kind of have figure out the right expression to work with. But now a computational version is not so obvious to prove. Like if you haven't seen a proof before, you probably stumble around for a while before finding one. Yao, as far as we know, didn't actually write down a proof of this. There's a nice survey of Goldreich, Nissan, and Vigerson from a little more than a decade later, which gave several different proofs of Yau's XOR lemma, each a few pages, and that's one non-trivial. But the one that I want to focus on is the one that uses Impagliazzo's hardcore lemma, since that will play a role later in the talk, and also illustrates this idea of reducing computational security proofs to information theoretic ones. Okay, and what the hardcore lemma says is that if a function is delta hard, then there's some subset of the domain, some hardcore set H, on which it's really hard. Okay, so specifically, the subset of the domain, its size, its density in the full domain is related to the hardness of G. It's actually of density 2 delta. Impagliazzo's original hardcore lemma had just a delta here. This correct version is due to Hollenstein with the factor of 2. And on this set H, what do we mean that G is really hard? I mean that it's indistinguishable from a random coin toss, an unbiased coin toss. All right? So if I look at X together with G of X, conditioned on X being in the hardcore set, that's computationally indistinguishable from choosing X at random from the hardcore set and just tossing a random coin. The way the hardcore lemma is usually stated is that G can't be predicted with probability much better than a half on the hardcore set, but by the equivalence of pseudo-randomness unpredictability, that this is an equivalent formulation of that. Okay, so another sort of a consequence of this is that if I now look at X and G of X on the entire domain, all right, not restricting to the hardcore set, it's computationally indistinguishable. I can construct a function H that's indistinguishable from G on the entire domain, meaning X G of X is indistinguishable from X H of X, where H is information theoretically delta hard. And what is that function H? On the hardcore set, it's a randomized function that outputs just a coin toss, a Bernoulli half. And elsewhere, it just equals G. Okay, and so now, like if you try to compute H with whatever your computing power is, outside H you might be able to compute it with probability 1. On H you're going to compute it with only probability half, and since H has density 2 delta, you'll have error probability delta. Yes?
H is fixed independent of the distinguisher.
Yes. This is H independent of the distinguisher. That's right. Right. So hardcore lemma is a really amazing theorem. Very powerful. All right. So once you have this fact, you can actually prove the conclusion of Yau's XOR lemma by saying, OK, I take this quantity that I'm interested in, the probability you compute G on K, an efficient algorithm computes G on K independent copies. By computational indistinguishability from H and a hybrid argument, I can replace all these G's with H's up to a negligible additive term, which we had in the bound, and then apply the information theoretic bound for H. OK, so that's the first example. I'm going to give one more example. And the kind of takeaway message is, later in the talk, will be multi-calibration gives you kind of an even more powerful and general tool for doing these kinds of reductions from computational security to information theoretic security. All right. Next example is from leakage-resilient cryptography. We have a lot of people in the room who are much more experts on this topic than me, but I'm just going to do a very simplified example from leakage-resilient cryptography. Suppose I have some secret, and I'll actually have it in 2 parts, K and R. So they're indistinguishable from uniform. And an adversary learns a little bit of leakage on the K part of my key. Okay, why might they only learn on the K part? Well, one of the common axioms, assumptions in leakage resilient cryptography is that only computation leaks. And so maybe you did a computation that only uses K, doesn't use R, and so that would be the opportunity for an adversary to learn something about K and not learn anything about R. Right? That's the Macaulay-Raisin, I think, sort of assumption in leakage resilient cryptography. All right, and importantly, it's the adversary only learns a small amount of leakage. So now think even just one bit of leakage. But what I'll say for the next couple of slides actually holds for a larger or up to at least logarithmic number of bits of leakage. Now the question is, how do I refresh my secret? Okay, because now, given what the adversary has learned, my key is no longer pseudorandom. If I try to use it for something useful cryptographically, I may not have security. And so an answer that I know from this work of Dembowski and Pietschak, maybe it goes back earlier in the leakage resilient cryptography literature, is the following. I can get a new key and R pair by applying what's called a randomness extractor to K. So I use R as the seed for the extractor and to kind of get good quality randomness. That's the idea out of this key that there's been leakage on. If you're not familiar with randomness extractors, you think of this as a hash function, where R is the kind of the index of the hash function from like a universal hash function family. So that's telling you which hash function you're applying that to K. And then, because you might get something shorter out of this, you apply a pseudorandom generator to stretch back to the appropriate length. Okay. And repeated applications of this idea with a K and an R and also another auxiliary L, let's say for left, repeated applications of the idea were used by Dembowski and Pietschak to construct what's called a leakage resilient stream cipher. All right, so let's think about how do we prove that from this we get a good new K-R pair. And again, we'll start with the information theoretic version. In the information theoretic version, the original K and R are not pseudorandom anymore. They're actually uniform. I'm better not use a PRG, so we'll just tolerate K prime and R prime being shorter than K and R, okay, because the PRG will immediately put us in computational security world. This proof is also quite easy in the information theoretic case. So K was originally uniform, and now I've leaked L bits on it. And so the entropy of K given G of K should be at least N, the original entropy, minus the length of my leakage. Now, it's important to pick the right way to measure entropy for the kind of for what follows. So we don't use Shannon entropy here. We use the notion of average min entropy of Dodis, Ostrovsky, Raisin, and Smith is a very clean one to use here. And so and this fact turns out to be true for average min entropy as well. And then the good thing about using average min entropy is that's like what, or min entropy, and then it also turns out to work for average min entropy, is that randomness extractors can convert things that have high min entropy into things that are close to uniform. And so if I apply a randomness extractor to K, and K has high average min entropy given G of K, then the output of the extractor is statistically close to uniform, even given G of K. All right, so G of K together with the output of the extractor is statistically close to G of K and uniform. And how much uniform bits do you get out? You get N, you get the min entropy, N minus L, minus something that's kind of how close to uniform you want to be. And so you can think of this epsilon as arbitrarily small polynomial, slightly negligible, and so you still get, compared to n, you get a lot of entropy out. Okay, so that's the information theoretic proof. What about the computational version? The tool that enables you to kind of derive a computational proof of security from the information theoretic one is the dense model theorem, which was done in joint work with Omer Reingold, Luca, and Madhur Tulsiani, which tells us, okay, we no longer can say that K given G of K has a lot of entropy. I mean, K even didn't necessarily, it was just only pseudorandom. So it doesn't have a lot of information theoretic, it need not have a lot of information theoretic entropy. It may have actually very low entropy. But what we can say is K is indistinguishable from some M, random variable M, that has a lot of entropy given G of K. Right? So originally, K was indistinguishable from the uniform distribution. So, but now, given leakage, is it still indistinguishable from something of high entropy? That's what the dense model theorem tells us. It tells us that actually, even given the leakage, K will be indistinguishable from something of the kind of entropy that we expect, n minus L. And now, again, we have a kind of very simple proof of computational security derived from the information theoretic security. So by the dense model theorem, the thing we're interested in, what the extractor does given G of K, is indistinguishable from, on K, is indistinguishable from applying the extractor on this dense model M, this model distribution M, given G of K. That's just by the dense model theorem. And now the latter thing is statistically close to uniform by the same argument that we had in the information theoretic proof of security. Yes, Yael.
The computational version works only if G is efficient. The information theoretic version, you can have G arbitrary.
No, G here is arbitrary. G does not need to be efficient. So that's important. In this dense model theorem, G does not need to be efficient.
Wait, so how do you, if G, okay, so if G is all powerful, it can kind of take off, like show that actually it can be kind of contain a proof that actually K has no entropy.
Let me. Yael's concern was asking, like, how can the dense model theorem be true even when G is not efficiently computable? And the point is that the leakage is short. I think that's the. So here, okay, dense model theorem, good. Thank you. I forgot to write. What I wrote on the previous slide held for any value of L. This only holds for L up to order log n or log of your security parameter. Yes. Thank you. Short leakage.
And also M is jointly distributed with K, right?
Yes, yes. And sorry, this random variable is jointly distributed with K, so that this like it's correlated here with G of K. Absolutely. Yes. Thank you.
Show up in the bound, there's some like degradation in the indistinguishability, and this is exponential in L or something.
Exactly, exactly. And that relates to kind of an open question at the end of the talk if I have time to get to it. Okay, so let me give a little sort of kind of history here. So in the kind of early 2000s, there was starting to be a really fruitful interplay between theoretical computer science and arithmetic combinatorics, additive combinatorics. Papers were starting to use results from those areas as kind of black boxes to build better randomness extractors in the Barak and Pagliazzo Vigderson, to analyze PCP constructions, to build certain kinds of pseudorandom generators for polynomials. And Luca had a conviction that there were some things that were happening in that arithmetic combinatorics literature that really had deeper connections with the concepts that we study in theoretical computer science. Not just like, okay, that's a powerful tool that we can import, or that their tools will be useful when we're studying some problem that involves groups or polynomials or the kinds of things they were studying. And specifically, he was intrigued by one of the main tools, lemmas in the proof of the Green-Tau theorem. All right, so the Green-Tau theorem says that the set of prime numbers have arbitrarily long arithmetic progressions. Okay. Doesn't seem like it has anything to do with, complexity theory. But the main, one of the main steps, key novelties in the Green-Tau proof, was proving that the set of prime numbers is indistinguishable in some sense from a subset of the natural numbers of constant density. And we already knew from Semeretti's theorem in the 1970s that all subsets of the natural numbers that have constant density have arbitrarily long arithmetic progressions. And Green-Tau kind of proved such an indistinguishability result with a kind of notion of indistinguishability that then allowed to deduce from Semeretti's theorem that the prime numbers must also have arbitrarily long arithmetic progressions. Yes?
You mentioned that the distinguisher here is additive distinguisher, and the property of being a prime is sort of multiplicative, and so this distinguisher is
I mean, so it's a good question.
What do you mean are indistinguishable?
I'm not going to try to formulate it. It's been a long time. Let me put both of those questions on hold because they're not important for this. Is sort of a detour in the talk, and if I spend time kind of reconstructing answers, we'll lose too much time, maybe on the break. So Luca thought this seems a lot like things that we study in complexity. The notion of obviously we study indistinguishability all the time in complexity and cryptography, and being indistinguishable from large subsets, that's like having high pseudo entropy. There should be some complexity theoretic analog. And in fact, it turned out to be true. So suppose I have let me put a picture here at the same time as stating the theorem. Suppose I have a distribution. I'm drawing it like a set, so think like uniform distribution on some set that's indistinguishable from the uniform distribution. So a pseudorandom set, pseudorandom distribution. And now I have some event which may not be efficient at all, right? It's an arbitrary event of some non-negligible probability delta in X. A subset, say, of X of probability at least delta. Then the dense model theorem says this X conditioned on this event, okay, there is some truly dense model distribution that's computationally indistinguishable from X conditioned on that event. Good question. Yes and no. Is it constructive was the question. Meaning there are proofs of this that kind of describe a way to build M kind of using distinguishers, like you assume by contradiction that there is no such thing. But the complexity of whatever description you get, which I won't be able to reconstruct exactly, is going to be higher complexity than the distinguishers that appear in this computational indistinguishability here. So you will see another phenomenon like that later in the talk. Okay, so this is the dense model theorem. I have a pseudo-random set or pseudo-random distribution, some subset or kind of sub-distribution of it of probability delta. It actually is going to be indistinguishable from something that is truly dense, right? Which is the same as having high min entropy. Right, and you get the formulation I talked about earlier, where I took X conditioned on some leakage. Let's think 1-bit leakage. I can have the event of conditioning on G being the leakage being 0, the event of the leakage being 1, and stitch those together to get the model that I talked about on the previous slide. Okay, and now you can see why short leakage or having only a small number of possible values of leakage will be important there. Also, if the leakage is large, these conditioning on the leakage will tend to lead to an event of negligible probability for which the dense model theorem doesn't apply. All right, so soon the dense model theorem was found to have connections to other things in complexity and cryptography. I already mentioned, actually as motivation, the leakage resilient cryptography application. And we saw also how it relates to computational entropy being indistinguishable from having high entropy. And then Impagliazzo showed that actually, so in the dense model theorem paper, we proved the dense model theorem using ideas inspired by the proof of the hardcore lemma. And then Impagliazzo showed a clever way of actually deriving the dense model theorem from an appropriately generalized version of the hardcore lemma. But Luca wondered, sort of still felt that there should be some deeper unifying principle here, and conjectured that the kind of really the right unifying principle had something to do with regularity. So now let me turn to talk about regularity theorems in graph theory and complexity. So the classic example of kind of a regularity theorem is Semeretti's regularity lemma in graph theory. This says, at a high level, every graph, right, no matter how complex, you should think of G as a dense graph. Sparse graphs, the statement will just be vacuously true. Every dense graph is indistinguishable in some sense from a graph of low complexity. So what is a graph of low complexity? All right, so we're giving the graph G, and then we have our indistinguishability parameter epsilon. The graph of low complexity, it's going to be defined by some partition of the vertex space into a small number of parts, where here small depends only on epsilon, or it doesn't depend on n, the number of vertices in the graph. And between every two parts in this partition, Vi cross Vj, our graph G is actually indistinguishable from a random graph of the appropriate density. And the appropriate density is the density, like what proportion of Vi cross Vj has edges from in G, like G's density. All right, and this is true for all pairs I and j, except for some epsilon fraction, where we kind of measure, this fraction is where we're measuring the pairs weighted by their density. The pairs, so the weight we put on Vi cross Vj is the density of Vi times the density of Vj, alpha j. So there's some exceptional pairs, and aside from that, G is indistinguishable from a random graph between all other parts. All right, so it's kind of low complexity in the sense that for many purposes, like we've reduced the description of this graph G on an arbitrarily large number of vertices to this number of parameters that depends only on epsilon, like these alpha parameters that are the, if we're thinking of just, sort of graph properties that are invariant under permutation of vertices, all that matters is the alphas, the densities, and the mu ij's. All right, so one downside of Semreti's regularity lemma is that the number of parts is actually, it's a function only of epsilon, but it's an enormous function of epsilon. It's a tower of height polynomial in 1 over epsilon. And in fact, for some versions of the, and it's known, Gowers proved that kind of behavior is necessary. And now, or I guess a decade ago, they even pinned down the right polynomial in epsilon. So 1 over epsilon squared, I think a tower of height 1 over epsilon squared, for an appropriately formulated version of the regularity lemma. There's several different, equivalent formulations that might lead to slightly different dependence on epsilon. Okay, so this tower, by the way, is, I don't know, at least for me, I think was a bit of a sort of psychological barrier that we'll come back to in a bit. So can there be a complexity theoretic regularity lemma? So with Luca and Madhur Tulsiani, we proved the following kind of complexity theoretic regularity lemma, which is that every Boolean function is indistinguishable from a low complexity function. But what we mean by low complexity is going to be pretty different, look different than what's in Semreti. So for every function g, and now let me make these functions that are bounded functions between 0 and 1, where we think of this as a description of a randomized function. So if it says 1/3 there, that means really we're thinking of, if g of x is 1/3, that means g of x is 1 with probability 1/3 and 0 with probability 2/3. I'll be more precise about that. So for now, just think of them as real valued functions. There exists, so I have a fix a function, a distribution on the inputs, a circuit size parameter s, and epsilon, and there exists a function that's low complexity in the sense it's computable by a circuit of size just a little bit bigger than s times poly 1 over epsilon, and is indistinguishable from g by all circuits of size s. Okay, so if I look at the expectation for every circuit f of size s, expectation f of x times the difference between h of x and g of x, that's bounded by epsilon. All right, this is kind of an unusual way for us to write things in cryptography. This kind of comes more from the way they do things in this arithmetic combinatorics. When they talk about regularity, they think of this as like an inner product between the f and the differences between the functions, f being nearly orthogonal to it. But an equivalent formulation that's more kind of cryptographer friendly is, instead of thinking of these real valued functions that I've written here, think of the corresponding randomized function. So h rand on x is 1 with probability h of x and 0 with probability 1 minus h of x. And then this is an equivalent way to write this is, say, the joint distribution of an input x and h rand of x is computationally indistinguishable from x and g rand of x. And computationally indistinguishable, I have this s epsilon here to just note by circuits of size s and with advantage epsilon. Okay, so some of this might look familiar to some of you. This is actually an equivalent. This latter thing is the statement of what's known as the leakage simulation lemma in leakage resilient cryptography. So also very useful for security proofs in leakage resilient cryptography. This is the special case for one bit leakage, which is captured here. The full leakage simulation lemma of Jetchev and Pietschak also considers more bits of leakage, again with like some exponential blow up in the number of bits of leakage. So you think of the leakage as logarithmic, and kind of optimizes the dependence on the leakage and epsilon and so on, which in some cases is better than what you would get using this. And all right, towards it being a unifying principle, we're able to use it to derive the dense model theorem and the hardcore lemma, and it seemed like a cleaner statement. There's no like assumption of hardness here. It's just a structure theorem about functions. Every function has a low complexity approximation, and now we use that to do various security proofs where we might have an assumption that G is hard or some distribution is pseudorandom. But one sign that it was maybe not quite yet the right unifying principle is that when we tried to prove the hardcore lemma, we didn't get the optimal Hollenstein 2 delta density. We only got hardcore density delta, which is kind of annoying to us. Like in particular, if you wanted to get the right Yau's XOR lemma from the proof I told earlier, the right bound there, you want the right hardcore density. All right, how does it relate to Semeretti or graph theory? Because that's what I motivated regularity lemmas coming from. There is a version of this, and actually what we prove is a version that doesn't restrict to circuits and bit strings as your input. You can have any domain for your input and any family of distinguishers that you're interested in for your second condition here. And then what low complexity means is that your function h, your low complexity approximator, is obtained by combining a small polynomial in 1 over epsilon functions from your distinguisher family. And it turns out that the way you combine them also can be done by a circuit of size poly 1 over epsilon. And then you can apply it in the graph theoretic setting by taking your domain. So if I have a vertex set of size n, I take my domain to be of size n choose 2, representing all possible edges that might be present in a graph. Okay, and then we can think of the function g, if this is our domain, and g is a Boolean function on the domain, as just the describing the graph, 0 or 1, according to is an edge present or not. And you can take the family of distinguishers to be family of all cut functions. Like for two sets of vertices, is there an edge between them? And it turns out if you apply this regularity lemma for that special case, you get what's known as the weak regularity, the Fries-Kanon regularity lemma for graphs. Right, so which is weaker than the Semeretti regularity lemma in the kind of indistinguishability it provides. But it's better in the sense the Fries-Kanon regularity lemma has not a Tower dependence on epsilon. It has only a 1 over epsilon squared dependence. And somehow, I think I mentioned this psychological barrier. One might ask this question, is there a complexity theoretic analog of like actual strong Semeretti regularity? And I would have said, of course not. Semeretti regularity has this Tower dependence, and that makes it useless for complexity theoretic and certainly cryptographic applications where we think of epsilon as like 1 over polynomially small or negligibly small. A Tower, if you pay that price in a security reduction, game over, like nothing, you get nothing useful out. And the answer is actually, that I want to convey is that actually, yes, there is a complexity theoretic analog of strong Semeretti, and that's multicalibration. Right? And that's work from Cynthia and Pranay and Rachel Lin and Daniel Lee that I'll mention some of the history later. So, all right, so what is multicalibration? Let's see how we're doing on time. So the multicalibration theorem says for every, I'll state it in the complexity theoretic form, for every randomized function on, say, bit strings of length n, every distribution on inputs, again, I have size and epsilon, there's a partition of the domain into only 1 over epsilon parts, so no tower appearing there, such that on each part, g of x is indistinguishable from a random function, like a Bernoulli of the appropriate parameter mu I. Mu I being just the expectation of g on that part. That's for, all right, so I have k plus 1 parts here, p0 to pk. There's some exceptional part, some epsilon portion of the domain where indistinguishability doesn't hold. And finally, the partition is low complexity in the sense that you can, given an input, you can tell which piece of the partition you're in using a circuit of size slightly bigger than s times poly 1 over epsilon. All right, let me draw a picture to make this statement still there. So I have the arbitrary domain, and the multicalibration, I have my function g. Sorry, I lost some of the animation I used to have here. It tells us that there's a partition of the domain, right, that's given to us. So originally we were just given g, the zeros and ones. It's a partition of the domain into a small number of parts. And on a part where g is nearly balanced, say here, it's indistinguishable. So here it's indistinguishable from, the g of x is indistinguishable from Bernoulli 0.6. Here it's indistinguishable from Bernoulli 0.9, so on. Yes?
The partition, you assume like you have a function that tells you if you're in the node is in there or not?
Yeah, so it's one way of doing this is a circuit that gives an input, gives you a number from 0 to k, and says, I'm in which piece of the partition you're in. All right, this condition is crucial. All right, so this multicalibration theorem would be trivial if we didn't have this. So we just say, OK, my partition is one piece is the zeros of g, one piece is the ones of g. Clearly on the zeros, g is indistinguishable from a Bernoulli 0. On the ones, it's indistinguishable from a Bernoulli 1. Right? But the point is that's not an efficiently computable partition unless g itself is easy to compute. Okay? And this is the theorem, the structure theorem that holds for all g, regardless of whether it's easy or hard to compute. All right. So this looks a bit like the way I formulated the hardcore lemma. Let's just contrast. The hardcore lemma, this holds for all functions. The hardcore lemma assumes that the function is hard in a particular sense, that it's delta hard to predict. Second, the hardcore lemma just tells you there's some subset of the domain where g is indistinguishable from Bernoulli half. This is giving you, covering the entire domain and saying everywhere the function g is kind of indistinguishable from something very structured, a random function. And finally, the pieces here are efficiently recognizable, and there's no such guarantee in the hardcore lemma. OK, so now let's contrast with Semiretti. So I've put in blue the places where the two statements are really the same or special cases of that same common generalization. The notion of indistinguishability can be formulated for both to be the same. That your indistinguishability from something of density given by the density of g, your graph or your function, is the same. And that you have some exceptional set of pairs or an exceptional part of the domain. That's really kind of the same. The two important differences. One is we've gone from a tower dependence to a polynomial dependence. And the second is what's our notion of low complexity? In Semiretti, the crucial aspect of low complexity is that what we have is a partition of the vertex set that induces then a partition of the edge space into these vi cross vj's. Which is different than what we have in our statement where we said your function on your domain and you have a partition on that domain. That corresponds in the graph theoretic setting to a partition of the potential edge space, the n choose 2. And to my surprise, but this is really out of the work of Cynthia Pranay et al. It's this insistence on a partition of the vertex set that is what incurs this tower dependence in SIMReady. And then finally, how does it relate to the weak regularity? From this, you can get a kind of your indistinguishable low complexity function to be the one that on an input x, you first compute which piece of the domain you're in, because that's efficiently computable by condition 3, and then you just output the expectation of G on that part, which you can hardwire in if we're working with non-uniform circuit complexity, which we are. Or you output a coin if you want to do the randomized function of that bias. OK, so because of time, maybe I won't. This came out of the algorithmic fairness literature. In their setting, the G is like some ground truth function that you're trying to learn, and H is a predictor that you've learned. And what multicalibration is saying, like even conditioned on your prediction, G and H are indistinguishable, and the way it captures fairness is that your distinguishers correspond to like demographic groups, subsets of the population that you might want to have fairness on. But I think since we're short on time, let me skip over that and just give, because this is not a talk on algorithmic fairness. So just some credits here. So the original multicalibration theorem, Herbert-Johnson, Kim, Reingold, and Rothblum, wasn't stated quite the way that I stated it. The first partition-based formulation, I believe, is in this paper of Gopalan, Kalai, Reingold, Sharon, and Wieder. Another important reference is connection, that psychological barrier I mentioned. Skorsky had a paper showing that you can use the complexity theoretic way of proving regularity and so on to give another proof of SIMReady's regularity lemma. And so maybe that should have been a hint that maybe there really is a complexity theoretic analog of strong SIMReady regularity. And then this paper of Dworkley, Lin, and Tankala that I mentioned is the one that really formalized this idea that multicalibration really is the same indistinguishability condition, like that it is a complexity theoretic analog of strong regularity. And then finally, the work that kind of got me into this with Silvia Cascuberta and Cynthia was pointing out that multicalibration is very useful for complexity and crypto applications. And since we have only a few minutes, maybe I'll just do one, or two quick examples. The point is, similar to SIMReady, now we've described our arbitrarily complex function in terms of just a small number of parameters, these mu's and alphas, the densities of the pieces of the partition and the expectation of G on those pieces. And in particular, you can just calculate how hard is G to predict on a uniformly random input, that same quantity that came up in delta hardness and in Pagliazzo. Well, it's the, on each piece, what's the best thing you can do? The best thing you should do if you're trying to predict G with the highest success probability is predict the majority value. Right? If it's, sorry, think about H. Sorry, H, the random function that G corresponds to. So think of the information theoretic hardness in H. On each piece, the best thing I can do, it's a Bernoulli coin toss. So my input gives me no information other than what piece of the partition it's in. And then I'm trying to guess a Bernoulli mu I. And if mu I is bigger than a half, I should guess 1. And if it's smaller than a half, I should guess 0. And then because G and H are indistinguishable, that strategy, the best strategy for computing H, is also the best strategy for computing G. All right? Up to a plus or minus negligible success probability. and up to a poly 1 over epsilon in circuit size. Okay, and similarly, you can like derive the hardcore lemma very nicely by just saying, okay, the way I'm going to get something that's very hard to compute is just rebalance on each of the pieces of the partition. So if G was very biased, if H is very, sorry, like in a place where G is very biased towards 1, if I upweight the zeros to make it balanced, then I become indistinguishable from a Bernoulli half, just like you want in the hardcore lemma. But it doesn't just do these things that are related to the hardcore lemma and delta hardness. You can also, for example, analyze the pseudo-Shannon entropy of g of x given x in terms of these parameters by just, again, calculating the Shannon entropy of the Bernoullis given x, just the average weighted by the alpha i's of the Shannon entropy of a Bernoulli mu I. And this is something that has come up in kind of work we did a while back on constructing pseudo-random generators from one-way functions without using hardcore bits. And then finally, let me just give a teaser. I think I won't go through the details. In a new work with Cassandra Markusson and Louis Potterman, I think Louis might be here. I saw Louis earlier, Cassandra, I'm not sure, is we apply multi-calibration to understand indistinguishability between distributions. And in particular, let me not explain how you apply multi-calibration, but basically you can reduce, we have two random variables. We want to understand how does their computational indistinguishability degrade as you take more samples. And we can relate it to the information theoretic problem of how computational indistinguishability degrades when you take more samples. And in particular, we're able to characterize this in terms of what's called the what we call the pseudo Hellinger distance. So information theoretically, Hellinger distance tells you if I have two distributions, how many samples do I need to take to distinguish them with constant advantage? That's given up to a constant factor by the Hellinger distance between those distributions. And now we have a computational analog of that statement as, again, as an easy consequence of multi-calibration. OK, so hopefully I've convinced you multi-calibration is a powerful tool for reasoning about computational hardness and indistinguishability. I didn't get to the examples but conveyed how it's a strengthening of these earlier ways that we had to reduce computational security proofs to information theoretic ones. And there's a bunch of open questions that I'll just leave for discussion on the break. And another takeaway from this is that we can continue to draw inspiration from Luca and the ideas he had. Thank you. Cynthia?
Your work with Cassandra and Louis, you talked about multiple samples. Any connections or things that we can get for differential privacy? On one database and X1 on the other?
Great. Cynthia's asking whether looking at multiple, this fact that we're looking at indistinguishability under multiple samples, whether there might be any applications to differential privacy. One guess is maybe one can derive composition theorems for computational differential privacy from composition theorems for information theoretic differential privacy. That's my first guess on it.
The multi-calibration theorem and many of these theorems are agnostic of the complexity of computing G, right? So this works for all G's. So if you now look at, easy to compute G's, ones that have circuits of size or something, does that, change the consequences, maybe stronger consequences somehow?
Yeah, so Vinod's asking, I said these are agnostic of G, and specifically we're using them to understand hardness, the hardness in G, various kinds of hardness, various kinds of average case hardness, like which may be this hardness of prediction, it may be this pseudo-Shannon entropy that I'm talking about, indistinguishability. Now, if G is like actually easy, yeah, so I'm not sure. Yeah, so I'm not sure in that region between. Like if it's easy, then the multi-calibration theorem is just vacuously true, right? You just partition into the zeros and ones. One kind of in-between thing I mentioned here as a kind of open problem is to have a uniform complexity analog. So everything I said in the talk was all in the kind of non-uniform circuit complexity. Circuits are your polynomially sized circuits. I believe there should be one. The settings in which the statement should involve some kind of easiness associated with G. So like maybe G is not easy to compute, but I can efficiently sample random pairs xg of x. So if you think of the example I gave of the least significant bit of the inverse on a one-way function, I can't compute G. If you give me an input, it's hard for me to compute the value of G. But if you want me to draw a random sample from xg of x, I can do that. I pick a random input to the one-way function, and then I have the value of G, and I take the output.